VC Chemistry, Unit 4, Outcome 3, Practical Investigations. In VC practical investigations, we're often asked to comment on one of the following 4 aspects of an experiment: validity, reliability, accuracy, and precision. So what is validity? Validity describes whether the experiment measures what it is intended to measure and whether the conclusion is justified. So we often think that validity is something to comment on about the results, but actually it is an evaluation of your method. So is your dependent variable changing completely due to you changing the independent variable? Or is it because actually there are some other variables that should be controlled but hasn't been controlled? Then it's also affecting your dependent variable. Okay, so if you have a variable, for example, if you're investigating the rate of reaction changing due to temperature, but at the same time you are also using different concentrations of solutions to investigate, then the changing in your dependent variable, in your results, you can't really distinguish what is causing the change in that rate of reaction. In that way, your experiment and your conclusion is not justified and therefore is invalid. Okay? Reliability describes how reproducible the results are. So by definition, you can only comment on reliability when you have more than one set of data. So your experiment has to be repeated for you to know if your experiment is reliable or not. Accuracy. Accuracy describes how close is the measurement to the true value. That also entails that you need to have a universally recognized value to compare it to. Right? For example, in the investigation to determine Faraday's constant, we are able to compare our results to the universally recognized one so that we can actually comment on how accurate our results are. And precision. Precision reflects the consistency of measurement, which is quite different from accuracy. So how do we distinguish between accuracy and precision? Well, if all your results are really close to true value and all close together, then your results are accurate and precise. If they are close together but far away from the true value, then your results is precise but not accurate. Sometimes your set of results can be really far away from each other, but if you take an average, it's quite close to the true value. So the data that is really low to the true value or really high to the true value sort of cancel each other out. Then in that case, your result is accurate but not precise. And of course, in the end, you can have neither. So let's compare the 4 students and comment on if their results are precise, or if their results are accurate. So suppose the true value of a measurement is 100.0. The first student got this set of data. You can see that the average is pretty close, and also the results, the 4 data, are very close to each other. So it's highly accurate and precise. The student B, you notice that all 4 of the measurements are quite close to each other, so it is precise. However, it's quite far away from the true value if you take the average. Therefore, it is low accuracy and high precision. And student C, you will see like merely the results doesn't really have any pattern in it, but if you take the average, it's actually quite close to 100. So this set of results has high accuracy because the average is exactly 100, but it's very low in precision because there's too much variation in the set of data. And then you will have a student who's neither precise nor accurate. Yeah? So precision and accuracy are actually measuring 2 different things. Then we have mistakes. Okay. Mistakes can be avoided. they're not errors when we talk about experimental investigation. So mistakes could be like a person misread the numbers on a scale, or not letting thermometer to take the solution temperature before the reaction starts, or you could have a residue of reactants left when they should have completely reacted. So in those cases, or sometimes you connected the electrode in the opposite way for electroplating. Those cases, if a measurement is taken after a mistake has occurred, then that measurement should be completely just rejected. It cannot be included in calculations. So taking average does not minimize the impact of a mistake. If it's a mistake, it should be kicked out. Then you have different errors, right? Errors still happen when you have done everything completely correctly, right? But somehow, due to certain factors, your result is deviating, is somehow different from the true value. So there are two types of errors we need to distinguish between: systematic error and random error. Let's talk about systematic error first. A systematic error produces a constant bias in the measurement that cannot be eliminated by repeating the measurement. So in most cases, systematic errors happen due to the way that you measure it, or due to the equipment that you use to measure it. Okay. So for example, if you use an electronic scale that measures 20 grams as 20.2, then it is quite systematic. Whenever you use it, it's going to give you a larger than true value. Or sometimes if you have a power source that gives 1.5A, well, when it displays as 1.4A, or the resistance given by a wire resulting in constant low values when we are trying to determine Faraday's constant, that will be a systematic error. It will always result in lower values when you calculate Faraday's constant. Or in titration, if a 20 ml pipette delivers actually 20.2 mils, or when in calorimetry, that a calorimeter that always loses heat. So essentially all calorimeter will lose heat. So those errors are introduced to your experiment, will affect the accuracy of the result, but they are systematic errors. They cannot be avoided. So how do we treat systematic errors? Whatever the cause, the resulting error is in the same direction for every measurement. So the average is either higher or lower than the true value. So in the exam, when they ask you how it impacts the measurement, you must say whether they ask you or not, you must indicate this systematic error will cause the results to be higher or lower. Systematic errors compromises accuracy, but it will not affect precision because it always skews the results to the same direction. Then systematic errors don't always compromise accuracy. For example, the error introduced by the electronic scales when we investigate Faraday's laws can be minimized by measuring the mass before and after, and because we're only using the differences in mass to calculate the final result, and therefore in that way, that systematic error will not impact the precision of your or accuracy of your results. Okay. Random errors. Random errors follow no regular pattern. The measurement is sometimes too large and sometimes too small. So for example, in the electroplating prac, the control of variable resistance to keep the current the same will result in random errors. Also, if you are judging a voltmeter or ammeter's last digit in measurement due to fluctuation, you can't control it, you can't avoid it. Sometimes you will read a bit larger, sometimes you will read a bit smaller, but that's fine. And the loss of electroplated material during washing and drying, you can't control it. Sometimes you will lose more than other times. Okay? Or some in calorimetry or enthalpy measurement, The difficulties in judging the fraction between 0.1 degree scale marking on the thermometer can also introduce random errors. So the effect of random errors can be reduced by taking the average of several observations. For example, in titration, we require concordant results to reduce random errors. Random errors will compromise both the precision and accuracy of the results.